diameter, mylar diameter, pitch diameter, thread pitch, and lead angle, include angle and contact height. And we also know for typical threaded fastener joint methods. Bolted joint, screw joint, stud joint, and set screw joint. We also studied strength analysis of screw joint. Okay. And this is the strength analysis of screw joint. For loose bolt joint without preload, we use this as strength criteria. And when the tightened bolt joint only bearing preload, we use this equation to calculate the working stress, and the calculated stress should less than the allowable stress. And D1 is the mylar diameter of the screw thread, and FA is the actual stress acting on the bolt. And if the bolt is subjected to preload and axial force, then we can calculate the stress on the bolt and stress on the members. And then we use this equation to calculate the actual stress, and this should less than the allowable stress. And if the bolt is subjected to preload and variable force, we can calculate the maximum stress, minimum stress, and stress amplitude. And we use this criteria, and it's under the condition the minimal stress is constant. If the bolt is bearing shear stress, we use this sigma p. To design, and the sigma p should less than the allowable sigma p. This is for the design and strength criteria. We use this strength criteria to design if we know the allowable stress or the safety factor and actual force on the bolt, we can calculate the Mylar diameter D1 or the diameter of the bolt hole D0 or the minimum of height between bolt and hole wall L min. Now, let's proceed to the next section, the design of joint of screw bolt group. In common practice, a group of bolts are placed in a specified pattern to form a multiply bolted joint to carry various external loads. In order to be convenient to processing and symmetrically laying bolts, ensure loading uniformly on the joint surface. And this is the uniformly layout of bolt group. When laying bolts, we should notice that for reamable bolt joint, don't lay more than 8 bolts parallel in the direction of the working load. And when bolt joint bear bending moment or torque, the location of bolts should near the edge of joint surface to decrease load of bolt. So this is reasonable and this is unreasonable. And when bearing axial load and big transverse load in the same time, special elements should be used to bear transverse load, such as P, sleeve, and pin. The average of bolts should have reasonable space, edge distance, and for prayer vessel, the distance between bolts should be less than the value recommended by the table below. For example, if the working pressure P is less than 1.6 megapascal, the distance between bolts D0 should less than 7 times D. D is the diameter of the bolt. And if the working pressure P is larger than 1.6 and less than 4 megapascal, the distance T0 should less than 4.5 times D. And the number of bolts distributing on the C cycle is usually chosen even number. And the material diameter and length of bolts in the C group should be uniform. In order to avoid board bearing additional bending load, we should avoid the following situations. For example, avoid uneven surface and avoid bolts or counter bolt structures and avoid inclined surface. When we do force analysis of joint bolt group, first we should find out the bolt which bearing the maximum force. And then calculate the strength of the bolt. We make some assumptions. The material diameter, length, and per load of all bolts are the same, and symmetry center of bolt group and centroid of joint surface are matched together, and joint surface remains plane after loading. The types of load analysis include first, bearing transverse load and bearing torque, bearing axial load, and bearing upsetting moment. For the first case, the joint bolt group bearing transverse load. The joint bolt group is subject to transverse load F sigma. We consider it in two situations. We know that for bolt joint, there are two ways to connection. The Riemann bolt joint and the ordinary bolt joint. For ordinary bolt joint, there is an coherence between the hole and the body of screw. And for the Riemann hole bolt, it have Riemann holes without appreciable clearance. So, for rimmed bolt joint, the diameter of the hole and bolt shank are exactly the same. The transverse load is thus carried by shearing and bearing of the bolt shank. Assuming each bolt is subjected to an identical load, the load each bolt carries is then F is determined as The total external transverse load divided by the number of the remnant bolt joint. And for common or ordinary bolt joint, there is a clearance between the hole and the bolt. The transverse load is thus carried by friction between the joint interface and ensured by clamping action of the bolt. Assuming each bolt has the same preload, then we have the F is coefficient of friction times QP. QP is the preload. Z is the number of bolts times I. I is the number of joint interface. So F times QP times D times I is the friction. Is the friction between the joint interface, and this should larger than Ks times the transverse force F sigma. Ks is anti-skid factor to account reliability. Universally select as Ks is from 1.1 to 1.3. And then we have this. The preload QP should larger than this, larger than the Ks times F sigma and divided by F times C times I. F is the coefficient of friction, and for cast iron or steel, select F from 1.1 to 1.2, and for coarse surface without measuring, universally select F from 1.3 to 1.45, and Z is the numbers of ordinary bolt. I is the numbers of and I is numbers of joint interface. For example, for the left joint, the numbers of clamped members is 2. So the number of interface I is 1. And for the right case, the bolt clamped 3, 1, 2, 3, 3 members. There are two interface. There are two interface. So
Loshi,
I read 2. Okay.
Loshi, can you go back the previous slide?
What?
Yeah, the previous slide. Can you go back one slide? Yeah,
This.
here. Okay, can you say it again? What is A Q P Z I?
FQPZI. Okay. F
Yeah,
is
yeah.
the core. F is the coefficient of friction. F
Mm-hmm.
times the force. F times force acting on the bolt. Is the we can calculate the friction. The friction. Okay.
Mm-hmm.
F times QP means the friction between the uh joint interface, and Z is the numbers of bolts. So this is for the friction of one bolt times Z is for all the friction for the all for the bolt group, and I is the number of interface like this. The interface is 1, and for this situation, the interface is 2. There, between the interface, there is the friction, and there is a friction. Okay, so
Mm-hmm.
the friction, the F times QP times Z times I means the friction between the joint interface of the group, and the friction should larger than the Ks times the transverse force, and Ks is the anti-skid factor to account reliability.
Or
Okay,
what?
Ks is anti-skid factor, a factor to account reliability.
Okay.
Okay, and QP is preload. Okay.
Okay. And another one, or is the same? So what if they are less than with each other? Then what will happen?
What?
This F Q P Z I. If they less than this K S and F, then what will happen?
Okay. If F times QP times Z times I, this is less than Ks times F sigma, means the friction between the interface is less than the transverse load. Okay.
And then,
And there
then
is
so.
so so there will have a relative movement between the clamped members.
Hmm.
Okay, the friction is less, means the friction is less than the transverse load, so there will be a relative movement between the members.
So if they less than, then there will be a relative moment.
Yes,
And if they are greater than, then there is no relative moments there, right?
yeah.
Okay, Lassie. Thank you.
Okay, and this is for the situation, the group bearing transverse load. And so the friction generating between joint surface after preload must more than the transverse load. And for the second case, the joint of both group bearing torque, like this, bearing torque T. We also consider it in two situations, the rimmed bolted joint and the ordinary bolt joint. When a multiply bolted joint carries a torque in a jointed plane, the connected members tend to rotate around the centroid of bolt group. Both ordinary bolted joint and rimmed bolted joint can be used to carry torque. When used ordinary bolted joint, the torque is carried by frictional force between the connected members. Assume that each bolt carries the same preload. From the equilibrium condition of torque, we have this F is the coefficient of friction. F times QP. QP is preload. And F, assume this, each bolt carries the same preload. Okay, QP is the same. And F times QP means the friction. Friction for one bolt. And the friction times the distance from the centroid to the center of the bolt. F times bolt means the we can calculate the torque caused by friction. So F times QP times R1 plus F times QP times R2 plus F times QP times RZ, or the total of torque caused by the frictions should large than Ks times the torque T to prevent relative rotate. And this is for the ordinary joint, ordinary bolted joint. It use friction to prevent to resist the torque. And we can calculate the preload should larger than this.
So Laoshi,
Yeah.
it means what you're trying to say is when we are screwing the bolt in the bolt at the bolt joint, the torque of the bolt should be less than the torque of the material.
The torque what?
The torque of the material should be greater than the torque of the bolt. Is that what you mean?
Sorry.
Actually, I mean those small holes. Actually, what are they? The small holes. Yes, yes.
Oh, yes, this holes represent the bolt joint.
So actually, what the blue one, the blue thing in the middle? What is that one?
Blue?
Yeah, in the middle, in the center. Yes, yes, yes. That's region.
Oh,
What?
this hole.
It's a hole.
Yes, it's a hole.
So actually, if it's a hole, how is it producing torque?
Okay. For this, like this shape, this blue means the hollow or a
Okay.
hole, and that means the bolt joint, clamping members, clap, okay,
Yeah.
and then it for this member, it's subject to a torque,
Mm.
torque. Okay. How to and okay. Let's see. Okay. How to explain? Okay. The torque may acting on this point or this point or this point to make the members to rotate.
You mean when we are screwing the bolt or the whole shape is rotating? Actually, do you mean the whole shape is rotating or just the screw joints?
Okay. Rotating means the members.
The members are moving?
Yes, the members are moving.
Okay.
Okay. And for the remnant bolted joint, the torque is carried by sharing and bearing of bolt shank. And also, assuming each bolt has the same stiffness, the shear load each bolt subject is proportional to the distance from the centroid to the center of each bolt. It has the same stiffness, so we have this Fi. Fi is the uh, is the force acting on the on the bolt divided by F1 divided by R1 is equal to F2 divided by R2, and it's equal to the F maximum divided by R maximum. The force taken by each bolt depends upon its radial distance from the centroid. That is, the bolt farther east from the centroid takes the greatest load, and the nearest bolt takes the smallest load. And from equilibrium conditions, we have this. The friction caused by F1 plus the friction caused by F2 and plus the friction caused by Fg should equal to the torque T. And combine these two equations, the maximum load a bolt subjected to is the maximum force is equal to the torque T times the maximum radial distance and then divided by the sum of Ri square. And this for the Riemann voltage joint group.
老师，
Yeah.
老师, can you please tell me what's causing that torque T? The torque T. Yes.
What
How-
what caused the torque T? Okay. For example, for this member, maybe maybe there is a force acting on there. Okay? Acting on there. So this member will rotate.
Okay.
Will rotate. So there is a torque T. And the torque T can calculate by the force times the distance between the force and the and there. Okay? The force times the distance.
Okay.
It can calculate the torque. If
So largely it means we are working on a body that is subjected to a torque to move, to rotate.
yes.
So it means only for this body, right? Or we have to apply the same thing for other bodies.
What?
This concept is only for this shape, or it's also for other shapes?
For
I mean, this concept, this ideology, this method, it's only for this kind of shape, or it's includes, you can use it for other shapes. I mean,
for another not only for this.
okay.
Okay.
Thank you.
And this is under the condition the group bearing torque and and then for the third case, the joint of both group bearing axial load. For example, like this, the both group bearing axial load F sigma. And if the total axial load F sigma acting on the both group is parallel with the axis of bolt and through the symmetry center, loading on each bolt is equal, and the working load or actual load of each bolt is the actual load divided by the number of the bolts, Z. And for a Riemann bolted joint and ordinary bolted joint, the calculation equation is the same. And usually, each bolt also bearing preload. If the preload QP is granted, the total load on each bolt Q is this. We studied this last class, okay?
Yeah.
And this is under the condition, the bolt group bearing axial load. And for the first case, the joint of bolt group bearing upsetting moment or overturning moment M. Okay, and assuming the overturning moment M is in the vertical plane before the bolted joint takes the overturning moment. All the bolts are preload. All the bolts. This means the bolt. Okay, all the bolts are preload and elongated equally, and the foundation or the connect member is compressed uniformly. And when the overturning moment M is applied to the multiple bolted joint, the bolt on the left side, the bolt on the left side of the y-axis will be strengthened further, and the foundation will be relaxed. And on the right side, the bolt will be pressed and the foundation will be compressed further. The force taken by each bolt depends on the distance from its center to the y-axis. And the bolt farthest from the y-axis takes the largest load, while the nearest bolt takes the smallest load. So we have this F1 divided by L1. L1 is the distance between the center of bolt and the centroid. Is equal to F2 divided by L2 and is equal to Fi divided by Li. And according to equilibrium condition, the total moment generated by the load in each bolt Fi should be balanced with the external moment m. Therefore, we therefore we have we have F1 times L1 plus F2 times L2 plus Fi times Lj is equal to the turning moment m. And this is the load of single bolt. While loading low upsetting moment, action bolt is A. It's A. While loading upset moment M, acting point of left bolt moved to B1 and C1. B1 is for the bolt, C1 is for the members. And action point of right bolt moved to B2 and C2. B2 is for the bolt and C2 is for the members. So for the for the left bolt, after loading upsetting moment, the force on the bolt will increase, and the force on the members will decrease. The members will be relaxed. And for the right bolt joint, the force on the bolt will decrease, and the force on the members will increase, because when for the right bolt, before loading upsetting moment, it's subject to preload. Preload may cause the bolt strength. So the bolt is subject to tensile stress, and and for the member on the right, it's subject to a compress. So and after loading upsetting moment M, the bolt will be pressed. Bolt will be pressed, and the force on the bolt will decrease, and the members will be compressed further. So the force on the members will increase. Okay, and then we can calculate the maximum force acting on the bolt. Use this. The M is the upsetting moment, and L is the maximum distance between the bolt and the y-axis.
Laushi,
Yeah.
I think it's time for break. But maybe when you finish this next one.
Okay, okay, have a break.
Okay,
Okay.
thank you. Mm.
Okay, let's continue.
Okay.
And when the group is subject to upsetting a member to prevent joint surface being crushed. We have this criteria. The J is the number of the bolt times QP divided by A, and A is the effective error of the contact surface. Plus M is the moment divided by W. W is the effective section modulus of the contact surface. And this should less than the allowable sigma p. And this equation is to consider the upsetting moment M and preload P. If the group is subject to axial or transverse force also, this equation should be modified. And then to calculate the sigma p minimum, and the sigma p minimum should larger than 0. And this table lists the allowable extrusion stress of material of joint surface, the sigma p for steel, cast iron, and concrete, brick, and wood. And the total tensile force on bolt, we use this to calculate, and this is the F maximum. Okay. And we consider 4 conditions. The types of load for the types of load analysis when the group is bearing transverse load or bearing torque and bearing axial load and bearing upsetting moment. And if the group is subject to transverse load, we consider two situations. When we use ordinary bolted joint, we have this to calculate the preload. And when we use Raymond bolt joint, we calculate the force acting on each bolt. And for Raymond bolt joint, the diameter of the hole and the bolt shank are the same, and the transverse load is carried by shearing and bearing of bolt shank. And then the load each bolt carries. Use this to calculate. And and for ordinary or its joint, there is a clearance between the hole and the bolt. So the transverse force is carried by friction between the joint interface. We also can use this equation to calculate the force distributed on each bolt. You can use for ordinary bolt joint. We can use this to calculate the force distribution on each bolt. But it use friction to resist the force. So we have this, the friction between the joint interface should larger than the transverse force. And then we can calculate the preload QP. And when the bolt group is subject to torque, there are two calculation equations, and this is for ordinary bolt joint, and this is for Riemann bolted joint. And when the group is bearing axial load, we can use this to calculate the actual force on each bolt, and F use this to calculate. And when the bolt group is bearing upsetting moment, we also use this equation to calculate the bolt, the load acting on bolt, and there is the maximum force. The maximum force can use this equation to calculate it. Okay, let's see an example. The example is the bolt group carries axial force like this. This symbol represents the bolt. Okay, and the group is subject to axial force sigma F. So we can, the joint of the bolt group includes 4 bolt joints, and the group bears axial force. So the load distributed on each bolt F is the axial force divided by 4. Okay? Any question?
Actually, please, can you go over that one again? This is axial force. I want to you to like re-explain again. I didn't really catch some things.
This is this means the boat. There are 4 boats. So the load distribution on each boat is external force divided by 4.
Okay, understood.
Okay. And this is the distribution force on each boat. There are 4 boats. Okay. And then let's see the example 2. Example 2. Compare the 3 layouts in figure using Riemann bolt joint A, B, and C. So first, the layouts of the 3, 1, 2, A, B, C conditions. This is the horizontal arrangement, vertical arrangement, and cycle arrangement. And the types of load. The joint is subject to a force R. So the R, this means the bolt. This symbol means the bolt. Okay. So the R is transverse force or axial force.
Actually, axial force.
Transverse force or axial force.
Axial force.
The R is transverse force, and the force R also can cause torque. The R can make the joint rotate. So the R can cause torque. Okay. So the bolt is subject to a transverse force and a torque. Okay. And then find the types of bolt joint. It's a Riemann bolt joint. And the centroid of bolt group for A, there is the centroid. B, there is centroid. And C, the center of the cycle is the centroid. Okay. And then the load distributed on each build is F1. F1 is caused by R, the transverse force. The transverse force distribution on each bolt is F1. And F2 is caused by the torque. The torque may make the joint to rotate. Okay, so for each bolt, it's subject to F1 and F2. F1 is the distribution of R. F2 is caused by torque. Any question? Okay, let's continue. And then for rimmed bolt joint, we have, let's see, the when it bears transverse loads for Raymond bolt joint, we use this to calculate the force distribution on each bolt. Okay. So for
Laoshi,
yeah.
Laoshi, can you go back the previous slide? Here I asked you what is F1 and F2 direction, but you didn't get me. Maybe my network problem.
Come back to which
Yeah, here. No. And then number 5.
number 5. Yes,
Yeah,
the load
here this F1. Yeah, what's the direction
F1.
of F1 and F2? Yeah.
F1 the bolt group is subject to a transverse force R. Okay, a transverse force R. So F1 is the distribution of the R on each bolt. On each bolt.
Oh,
Okay.
distribution of each board.
Yes, the distribution of the transverse R on each bolt.
So this is not one kind of force. This torque.
Okay. Okay. It means there is, you can see. Okay. For example, for this bolt, okay. For this bolt, this is the F1.
Oh,
F1.
okay.
Okay.
And what
F1.
about F2?
And F2 is caused by torque because this R is not on the centroid. It's not acting on the centroid. Okay. So the R may make the joint to rotate.
Yeah.
Rotate. Okay. So it's okay. Subject to 转动的话bolt. This is the F2. This is F1. This is F2. Okay. This is
Okay.
F2. This is F1. This is F2. And for the right bolt, this is F1 caused by R. F1. Okay.
Okay.
And this is the F2 in this direction because the rotation is around the centroid. So this is F2. Okay. The
So here
direction, the direction is different.
Oh,
Okay.
confused.
Okay. And this is F1, this is F2, this is F1, this is F2. Okay. And then we can calculate the F1. F1 is a transverse force divided by the number of the bolts. The number of bolts is 3. It's 3, okay? is 3, both 3. So F1 is R divided by 3. Okay. And then the torque T is Fi times Ri. We have this equation. Okay. And Fi is the force acting on each bolt to resist torque, and Fi depend upon its radial distance from the centroid R. Okay.
Yeah, Lucy.
Okay. So this is for the layout A. This is the direction of F1. This is a direction of F2. And for the second bolt, it's subject it's subject to the F1 caused by the transverse force R. And F2 because the second point is on the centroid, so F2 is 0. F2 is 0, okay? And this is the direction of F1 and F2. F1 is caused by R. F2 is caused by the torque. Okay? So for the left bolt, the total force is F1 minus F2. For the second bolt, the total force is F1. For the third bolt, the total force is F1 plus F2. And and R, the distance between the bolt and the centroid R is A, the distance. So the torque T, we can calculate torque T is the sum of Fi times Ri. So for the second so for the second bolt, the R is 0. So T is equal to 2 times distance A times F2. F2 is caused by torque. Okay. And the maximum force acting on bolt is there. F1 plus F2. So this bolt carries the maximum force in layout A. Okay, and for layout B, this is the direction of F1. F1 caused by R, and this is the direction of F2. And for the second bolt, it's on the centroid, so F2 is 0. And for this bolt, this is the direction of F2. Okay, and we also have this. The torque T is 2 times distance A times F2. And for layout C, this is the direction of F1, F1, F1. And this is, for this bolt, the direction of F2 is horizontal, is this. And this is the direction of F2 for this bolt. And for this bolt, the direction of F2 is there. F2. Okay. And the torque is 3 times the distance A times F2. Okay. And the resultant force F, we can use this to calculate. And the cosine alpha. When alpha decrease, the cosine alpha will increase. So for this, for the layout B, the alpha is 90 degree. So this bolt and this bolt carries the maximum force, and alpha is 90 degree. Cosine alpha is 1. Okay. Cosine alpha is 0. Okay, is 0. And and for this this alpha or this bolt, the alpha is the smallest, so cosine alpha is the largest. So this bolt carries the maximum force. Okay, what's the maximum force? Okay, any question?
No question, Loshi.
Okay. Okay. Let's see the example 3. The bolt group. We use the rim and the bolt joint. The connection scheme is shown in the finger. We know that the transverse force is 12,000, and the distance between the centroid and the force is L. L is 400 millimeter, and A is 100 millimeter. So compare the maximum transverse force on both in the two layouts, and compare which bolt arrangement is reasonable. Sorry, wait a minute. Okay, let's continue. So we know that the type of the bolt joint is Raymond bolt joint, and we know the transverse force and the distance between centroid and the force, and we can calculate the distance between centroid and the bolt. So first, we should calculate the maximum transverse force on bolt in the two layouts, and then compare which bolt arrangement is reasonable. Okay. First, simplify the load. Simplify the load, we can obtain that the joint is subject to a transverse force F sigma, and the transverse force may cause a torque. So, there is a transverse force and a torque. We can calculate the torque. Use this, the force times the distance. We know the force and the distance, so we can calculate the value of the torque. And then determine the transverse force on each bolt. Okay. The transverse force on each bolt will use Fs1. Use this represent the transverse force on each bolt. Okay, any question? Any question? So,
No, Loshi.
see? Okay, this
Tashi,
is the
can you go over that one again?
which
How you were able to get the angles for the circular joints?
how to what?
How to get the angle denominations for the circular holes? Yeah.
Three? Okay. How to what?
How to get the transverse force on each bolt?
Oh, how to calculate the transverse force on each bolt?
Yeah.
Yes. This is the bolt joint is Raymond bolt joint. Okay.
Yes.
Raymond bolt joint. So we can find the summary there. When the group is bearing transverse, okay. It's bearing transverse load. Oh, no. What's wrong? Bearing transverse load.
Yes.
Okay, this. For rimmed bolt joint, we use this to calculate. This to calculate the force distribution on each bolt. Okay?
Okay, Lashi. Hold on,
Yeah.
I'm coming. I'm in class.
What?
Nothing, Loshi. Continue.
Okay. Okay. For layout A and layout B, we can calculate the transverse force distribution on each bolt is the transverse force, the total transverse force divided by the number of the bolts. For layout B, there are two bolts, the 4 bolts, and for layout B, there are also 4 bolts. So we can calculate FSL is the total transverse force divided by 4. Okay, it's 300 Newton. So this is calculation of the transverse force distribution on each bolt, and this is the direction of the FSL. Okay, FSL, and then and then for the Tokyo, The bolt is used shear force to resist torque T. Then we should calculate the shear load each bolt subject. Fs to A. Okay, this is for layout A. For layout A, we have the distance between the centroid and the bolt itself. Is square root a square plus a square. So we can calculate the distance between the bolt and the centroid is 141.1. Okay. And we can use this to calculate the shear load on each bolt. It's the torque times RA. RA is the distance, and divided by the sum of RA square. And we have calculate the torque. The torque is the force times the distance L. So we can calculate the shear load on each bolt. Use this equation, okay? Use this equation. This equation you can find for torque. Use this to calculate the maximum shear load on the bolt because the distance is the same. For layout A, the distance R is the same. Okay. And then so we calculate calculate the shear load. And this is the direction of shear load Fs2A. So we can calculate the total force. Use this equation, okay? Use this equation. So for the maximum force, we should find the minimal alpha, okay? And for layout A, for bolt 1, the alpha between Fs1 and Fs2A is 45 degrees. And for bolt 2, the alpha is 45 degree also, also too. And for bolt 3 and 4, the alpha is 135 degree. So bolt 1 and bolt 2 carries the maximum force, and then we use this to calculate the maximum force. Is Fs1 square plus Fs2a square plus this, and alpha is 45 degrees. Then we can calculate the maximum force for layout A is this. And then for layout B, we have the distance. The distance between the bolt and the centroid is A is 100. And we also can use this to calculate the FS2B. There is a little should modify there. FS2B to calculate FS2B is caused by the Tokyo. And then we can say that the layout, the bolt 1 carries the maximum force. Is the Fs1 plus Fs2B. So the maximum force for the layout B is this. So this is the maximum force for layout A, and this is the maximum force for layout B. To compare the two layouts, we can know that the maximum force for layout A is less than the maximum force of the layout B. So layout A is reasonable because the force is smaller. The force is smaller. Okay, any question? Okay, any
Yeah,
questions?
Loshi. Here, how you got this angle 45 degree for F1 and F2?
F
The pre
F
the previous
one
the previous problem. Yeah,
F1 and F2.
yeah. Uh,
You means this
mm,
FS1 and FSA2.
yeah. But
Okay.
not this one. The previous one.
FS1 is the distribution of transverse force. Transverse
Hmm.
force. Transverse force is this direction. Okay. And it's distributed on each bolt. So this is the direction of FS1. And for Raymond,
No, go back, Loshi. Can you go back?
go back.
Yeah,
Go back to where?
previous slide.
You mean there?
Yeah, here. Why you used only FS1 and FS2? Why not
FS. Why not what?
this cos alpha equal 45 degree? That one.
Uh, you mean
Down.
how to calculate FS1 and FS2?
No. This
No.
F max equal
The
root of
oh oh
F.
oh Oh, the maximum force, you mean?
Mm-hmm.
The maximum force, okay? Okay. For layout A, there for the bolt 1, this is the direction of FS1, okay? This is the direction of FS2A, okay?
Mm.
Because the joint will rotate around the centroid, okay?
Yeah, yeah.
So this is the direction of this. So this is the resultant force, okay, of
Yeah.
FS1 and FS2, and also there is the resultant, and what there?
So so every time these two force they are acting like in 45-degree. So they are not changing their.
Yes, for
Did you get me?
3 and both 3 and both 4, the alpha is 135 degree.
Hmm.
So the cosine alpha is
45.
no. Cosine alpha, if alpha is 135 and cosine alpha is minus, okay?
Okay, yeah.
For 3 and 4 both, cosine alpha is minus.
Hmm.
Okay? Cosine alpha is
Please,
minus.
Lashin,
And yeah,
please, I have a question. In the formula of F max, yeah, I want to know if the square is for FS2A or just for A.
or FS2A, what's you want to know FSA use this to calculate.
I mean,
Sorry? Use
okay, it's okay.
Use this equation to calculate FS2A. FS2A is depend on the distance between the bolt and the centroid. And
Okay.
for the layout A, the distance is the same.
Mhm.
So the FS2A is the same. And for the maximum force, the bolt 1 and bolt 2, the alpha is 45 degree is the maximum. And for the bolt 3 and 4, the cosine alpha is minus. This is the resultant force is less than this. So the maximum force is on bolt 1 and bolt 2, and use this to calculate the maximum force. Okay, any question?
What about bolts 3 and 4? It should be same force, right?
Bolt 4, you mean bolt 4?
Yeah, 3 and 4. Yeah.
Okay, for bolt 4, then the alpha is also 135. So cosine alpha is minus. And this is the resultant force. Okay? It's
Uh,
more is smaller than this. Okay?
Okay.
This is
why is it smaller? How you get it?
okay. Do you know how to find the resultant force?
Resultant force. That formula? Hello.
Yeah. Okay. Okay, let me see. Well, there. Okay. For the two force F1 and F2, if you want to find the resultant force, then we can draw a parallelogram. Okay. And this is
Resultant.
this is the resultant force. And how to
Yeah.
calculate the resultant force?
Yeah.
We use this. We use this equation to
Mm.
calculate. Okay.
Mm.
Use this equation
Yeah.
and alpha is the angle between F1 and F2. Okay.
Yeah.
And there, this is the alpha between FS1 and FS2A. The alpha is 45 degree. Okay,
Mm.
it's
Okay.
45 degree because, okay, sorry. It's, the bolt is on the cycle, okay?
Mm-hmm.
Okay, and this is the direction of FS2A, FS2A, okay? FS2A.
I think it's the same direction for FS1 also, right?
What?
There's the same direction for FS1 also.
Yes, FS1 is this direction. It's
Or
this
vertical. So,
direction vertical. It's vertical, and
mm-hmm.
and this is the direction for FS2A, and
Yeah.
yes, and this is vertical, so the angle is 45 degree. Okay,
45. Mm-hmm.
it's
Okay.
it's 45 degree. This angle is 45 degree because this direction is vertical. So we can calculate the maximum force use this. Any question?
No, Lucy.
Okay, so let's have a break. Okay?
Yeah, yeah. Yeah, Lucy. Okay.
Yeah.
Yes, Martin.
Okay, let's continue.
Okay, Lausi. Let's
Okay.
continue.
So, okay, let's continue.
Yeah,
So, you should master the summarization of the load analysis of the four types of when it bearings when it bearings transverse load or torque or axial load or upsetting moment. When the bolt group is subject to axial load or upsetting moment, the calculation for Raymond bolted joint and ordinary bolted joint is the same. You can use these equations to calculate. But for transverse load and torque, we also can use the equations for Raymond bolted joint to use these equations to calculate the distribution of force on ordinary bolt. But the force F is not directly the actual force of the ordinary bolted joint because it's not use the shear force. It's not use shear force to resist transverse load or bearing or torque. It uses friction. It uses friction to resist the transverse force and the torque. So the distribution force, we can use this to calculate for ordinary bolt, but we use this equation and this equation, use this equation and in this equation to to ensure the design is reasonable. So the friction should larger than the force caused by transverse load or torque. Okay, understand? Understand?
No, Lausi. Can you say it again?
Okay. Good. For Raymond bolted joint, it uses shear force to resist transverse force and torque. Okay. Use shear stress. So we can calculate the shear stress. Use this and this. Okay, for Raymond bolted joint. But for ordinary bolted joint, it uses friction. To resist transverse force and torque. So it should satisfy this equation and this equation. The friction is larger than the transverse force, or the friction or the torque caused by friction should larger than the external torque T. So for ordinary bolted joint, it should satisfy this equation and this equation. But we can use, okay, what's wrong? We can use this equation to calculate the force distribution for ordinary bolted joint, and use this to calculate the force distribution for ordinary bolted joint. but use this to calculate the force distribution. The F is shear force, but for ordinary bolted joint, there is low shear force. It uses friction. And this only means the distribution of force, not the actual force on the bolt, on the ordinary bolt. Okay. Okay.
Okay.
So let's say the example 4. A rectangular steel plate is fixed to the channel beam with 4 ordinary screws. 1, 2, 3, 4. 4 bolts. And we know that the transverse force R is 10,000, and the distance between the R and centroid L is 600 millimeter. And we know anti-skid factor Kf is 1.2, and the coefficient of friction F is 0.3. Number of joint interface I is 1. So calculate the preload QP. And this is for the ordinary bolted joint. So we should calculate the QP. Okay. So first, we simplify the load. For the joint group. It's subject to a transverse force R. Transverse force R, and the R may cause a torque. T. So all the bolts is subject to a transverse force R and a torque T. Okay? And then under torque T, the transverse force distributed on both the under or the shear force. Under torque T, the shear force. We use this to calculate the force distribution for ordinary bolted joint. Okay. Under T, the shear force distribution on bolt is, we can calculate the FST. FST is the force distribution caused by the torque. The calculation equation we use the Riemann joint bolt. Use this to calculate FST. And for the force, FSR is the force distribution of the transverse force R. We also use this, the transverse force divided by the number of bolts to calculate. Okay, understand? Understand?
Yes, Lord.
Okay, we use the Riemann bolted joint, the equation of Riemann bolted joint to calculate the force distribution. So we know that for the point 1, 2, 3, 4, the direction of FSR is vertical. Okay, it's vertical. And the direction of the FST, this is the direction of for bolt 1, and this is for bolt 2, this is for bolt 3, and this is for bolt 5. 4. So we can find the maximum force. So for which bolt the force distribution is the maximum? The bolt 3. Okay. The distribution on bolt 3 is maximum. It's FST plus FSR. Okay. Any question? Any question?
Rashid,
Yeah.
the load on the boat 3 is maximum.
What?
You said the force on the third boat is maximum. Why?
I said what? I can't hear.
The force in volt 3, how it become the maximum and why?
Okay. How to find the maximum force? You mean how
No,
to find the maximum force? Okay.
you said
Yeah.
volt 3 is the maximum force, but how is
Bolt.
maximum?
So why the bolt 3 carries the maximum force?
Maximum, yeah.
Yeah. Because you can also okay. Use this equation to calculate. So the alpha is the angle between the two forces. For one, alpha is 180 degree. Okay. Okay. So cosine alpha is -1. Okay. Cosine alpha is -1. Okay. And for both 2 and 4, alpha is 45 degree. So cosine alpha is square root 2 over 2. Okay. And for both 3, alpha is 0. So cosine alpha is 1.
Oh.
Cosine alpha is 1. Okay. So cosine alpha for both 3 is the maximum.
So we need to follow the this figure, right?
Yeah. Yeah. The alpha is 0 for both 3. So the resultant force is the maximum. Okay.
Yeah.
Okay. So calculate the maximum force is FST plus FSR. So then we can calculate the maximum force distribution on both 3 is this. Okay. And this is and the maximum force is a shear force. But it's ordinary screw. So we use this.
Can you go back, Flash?
Go back.
Here,
Okay.
T R max divided by 4 R square. This 4, it should be Z, or why this 4? Because of 4 screw?
What?
In the formula, this 4.
4.
So, yeah.
4.
This 4. It's because of the 4 screw, or there's the fixed formula?
Yeah.
Not this one. FST.
This
The
4.
first one.
The Z is the number of bolts.
I'm talking about here.
There are 4 bolts. Okay, there are 4 bolts. So J is 4. Okay,
I'm talking about the first line, FST.
FST.
Yeah.
FST. Okay.
This 4 is from formula or because of 4 volt?
We use this. We use this to calculate
Oh yeah. That I'm asking. Okay. So
to calculate the force distribution, and the distance r is the same, and
yeah, that's fine.
I
Get it. I get it. It's okay.
expand it
Okay. I got it.
4.
Yeah.
Okay, and then we can calculate
Yeah.
and then calculate the maximum force distribution on both 3. So for both 3, it's subject to shear force, to shear force. For its ordinary bolt joint, so it have this equation. This equation, okay? With this equation, it's the bolt 3 is subject to shear force. This means the shear force, and then QP should larger than this. This is for the bolt 3. So we load the KF and F and I, and we have calculated the maximum force distribution on the bolt 3. And then we calculate the preload should larger than this. Okay? Any question?
No, Rafi.
No question.
Okay. Okay. Okay, let's see the exercise. To simplify the load, there is a external force FQ, and this is the direction of FQ. The angle between the FQ and the vertical is 45 degrees. So simplify the load. So you have 5 minutes to simplify the load, okay?
Logic, these two figures is different from one another, or the same figure?
Okay, have you finished it? Okay.
妈妈，下面不好玩，太不好玩了，下面好热的，太不太好热了，我好热呀。
So first, let's resolve the external force FQ. It's a vertical force
妈妈，妈妈，我
and a horizontal force. Okay? Resolve the force FQ to vertical force and horizontal force. And the vertical force is transverse force. Okay? It's transverse force. Okay? And the horizontal force is axial force. Okay? This force is axial and this force is transverse. Okay? And then
Which one is transverse, Loshi?
what?
Which one is transverse, you say?
The vertical force. The vertical force is transverse force. And this force Ft is transverse force in this direction. And this force Fa is axial force. Okay? This is the board there. And this is the transverse force. And this is the axial force. Okay? And you can see? And then we can calculate the transverse force. It's the FQ times cosine 45 degree. And you also can calculate the axial force. It's FQ times sine 45 degree. Okay? The FQ can be resolved into a transverse force and an axial force. And then both the transverse force and the axial force may cause a upsetting moment M. Okay? So this transverse force times the distance between the transverse force and the centroid is A prime. It's A prime. So A prime times the transverse force is the upsetting moment caused by the transverse force. And the axial force also can make the upsetting moment. And it's the force times the distance A. So the moment M is the moment caused by transverse force plus the moment caused by the axial force. Okay? Any question? Any questions? If there is no question, we'll proceed to the next section, okay? Okay, this section is the design of bolted joint. So we should first decide the number of bolts in a pattern and their layout, and then simplify the dimension and materials of the fastener. This is the structure design. This needs force and strength analysis. And this is the material and allowable stress of bolt. Usually for bolt, the material we choose carbon steel and alloy steel. And the selection of material for thread fasteners is normally based on the requirement of strength, weight, life expectancy, and cost, and corrosion resistance, and stress. We use stress to determine the property classes. And this is the property classes for metric fasteners. And the table details mechanical properties of different property classes for metric fasteners. The strength of steels for bolts and screws is used to determine property classes. Property classes are identical by a numerical code system ranging from 4.6 to 12.9 to represent the strengths. The numeral before the decimal point is the tensile stress divided by 100. And the numeral following the decimal point is 10 times the ratio of yield strength to tensile stress. For example, a property class 4.6 implies that the tensile stress is 400 megapascal and the ratio of yield stress to tensile stress is 0.6. So we calculate the yield stress is 240 megapascal. And this is the property class. And this is the size range. For property class 4.6, the size range is from M5 to M36. And this is the minimal proof strength. And this is its material. You can use low or medium carbon steel. You can find the table in your textbook. And then the allowable tensile stress is decided by sigma s divided by safety factor. And this is the allowable shear stress and extrusion stress. This is for steel, and this is for cast iron. This is for ductile material. This is for brighter material. Okay, and and safety, and this paper is for the safety factor. The safety factor is selected as selected under different conditions, and for loose bolt joint, we select safety factor from 1.2 to 1.7. And this is for the ordinary bolted joint, and this is for the Raymond bolted joint, and this is for static stress, and this is for variable stress. And this is means don't control the preload, and this means to control the preload. Okay. And this is the allowable extrusion stress and relative stiffness. Okay. And this is the coefficient of friction F. So the design procedure include design the pattern of bolt layout and the number of bolts in the group. It's to ensure each bolt within the group is uniformly loaded, or to minimize the maximum load a bolt carries. And then analysis operating loads on the bolt joint. Resolve the loads into simple load conditions, that is tensile load, shear load, torque, and moment. And then determine the load each bolt subject to according to the bolted joint type, its ordinary or rimmed, assembly condition, with or without preload, and the load condition, transverse or axial load, static or alternating load. It's first to determine the forces act on each bolt by each applied loads separately. Identify the bolt that carries the greatest load in the group. And then determine the critical section dimension using the Miller diameter division according to the design criteria to calculate the Miller diameter division. And then decide the size of bolts, lugs, washers, and so on. It's according to the design handbook. So for the structure design, the bolt layout is usually designed as a simple systemic geometry, a square, rectangle, or circle, and then select an even number of bolts in a group. And each bolt has the same size, thread series, material, and property class. And ensure rational arrangement of bolts. A sufficient room should be provided, and the coarse surface to be joined by a bolt should be machined. Let's see the example. Example 6. A sliding bearing. This is a sliding bearing. It's bolted to a smooth floor. The bearing is supported to carry a load F. applied at the middle of the bearing wings, and the angle between the force and the horizontal line alpha is 45 degrees, and detailed dimensions are shown in the finger. The H, the wings, and the length. We know that the coefficient of friction between the bearing bottom surface and the floor is 0.16, and the allowable bearing stress between the bearing and floor, sigma p, is 125 megapascal. So, select proper bolts for the connection. So we can use this procedure, and then first we should do the structure design. Propose the number of bolts and pattern, and from this finger printed structure, we choose two identical bolts, there and there. And then a tightening torque is also applied. Then do the force analysis. First, determine the forces on bolted joint, each subject to a force F, and the direction between the force and the horizontal line is 45 degrees. And then we resolve the force into vertical and horizontal components. This is the vertical is axial force, and the horizontal is shear force on the joint. And then we can calculate the axial force. Use this. The axial force F sigma V is F times sine alpha. Alpha is 45 degrees. And then calculate the shear force on the horizontal direction. And the shear force is F times cosine alpha. Alpha is 45 degrees. So calculate the axial force and the and the horizontal force. And then the horizontal force or the shear force may cause overturning moment. And then we can calculate the overturning moment M. We use the shear force 2 times the distance. The distance between the horizontal force and the centroid is 150 millimeters. So we can calculate the M. This is the overturning moment. So we simplify the force into axial force, shear force, and overturning moment. And then determine the forces on each individual bolt under the axial force. Under the axial force, the force distribution, we use this. The axial force divided by the number of bolts. So the number of bolts J is 2. J is 2. So we calculate the force distribution. Sorry. Wait a minute.
No problem, Lord.
No. And this is for the force distribution of the axial force. It's the total force divided by the number of bolts. The number of bolts is 2, okay? It's 2. So we calculate the axial force on each bolt is this. And then we calculate the maximum force caused by the moment m. You can use this equation. You can find this equation. Okay, use this to calculate the maximum force caused by overturning moment m. And and then the total axial force, the force caused by overturning m is vertical. Okay. For the left is this distance. It's up is this distance, and for the right is this distance. Okay, this distance. So the total axial force acting on the left is the maximum. Okay, and you can see for this bolt, the working force is maximum. And you can see.
No question, Lord.
Okay, okay. So the maximum force for the left bolt is Fa plus F max. Fa is the force distribution of the axial force F sigma V, and F maximum is caused by the moment m. It's actual force. And for the shear force, F sigma H. F sigma H. We have this. It's the the bolt is ordinary bolted joint. It's ordinary bolted joint. So under the shear force or transverse force, we have this. You can find that this is a little different from the from there for transverse. No. Yeah. Not there. F times QP, CQP. F times CQP should larger than that. Okay, find in the
你别看我，别看我，刚才你手机在响。
F times QP should larger than this. Okay, it's for the condition. It is bearing transverse load. Okay, it's different. You can find there is a little difference. Okay, it have the difference is there. Okay, first this F sigma V is the total axial no not sigma V. There is a little wrong. F sigma H is the total transverse force. So these ordinary bolts should use friction to resist the transverse force. Okay, there is H, not V. There is H. So the friction, this is the friction caused by the preload. But there is also axial force. Okay, the axial force may make the members relax. This is the direction of the axial force acting on the left bolt. It will make the interface relax. So it should Maller's this. This means the axial force distribution on the members. So the friction is the preload Maller's this. This will make the joint and the floor to separate. So Maller's this, and then we can calculate the QP. There is lot V, the H. There's a little wrong. There is H, not V. And then the QP should larger than this. And then we calculate the QP and we lose the force, the actual force acting on the bolt. Then we can calculate the total force the left bolt is subject. Use this equation to calculate. And this is the total force. And then we determine the diameter of the left bolt. First, we select the bolt property class as 4.6. And then the yield, we can go the yield stress, sigma S, calculate the sigma S. And assuming the safety factor S is 1.5, the allowable stress is sigma S divided by S. So we can calculate the allowable stress. And then we use this equation to calculate the minimal diameter D1. is 12.7 millimeter. And then we select the major diameter D is 16 millimeter. And then we use this to check if the design is satisfy this this to prevent crash failure of right bolt. And this is the effective error and and this is the effective section modulus is less than the allowable sigma p, so it's allowable, and then we should satisfy the sigma p minimum larger than 0. So the design you choose this is reasonable. It's reasonable. And this can find from the handbook for this major diameter bolt. The minimal diameter is 13.6, larger than the calculated D1. Okay. Any questions? Any questions?
No question.
Lashi, are you following our textbook or any reference book?
For what?
The PDF the office give us. So are you following this book? Because this PPT, like if you want to find something in your book, but like for me, I can't find it. So which book are you following? Can you please share with us?
You want this PPT?
No,
Do you
Yeah,
mean
this PPT also, even the book.
the book, the handbook? You mean the handbook?
Yes.
Yeah.
Okay, the handbook is very thick. Okay, I can't give you the handbook.
Okay, Laoshi, can you
Sorry?
share this PPT, please?
This PPT I have sent
I've
the
already shared it.
PDF. I have sent the PDF moment to the group.
Yeah.
Okay.
Last year.
Sure.
Suhan, you can go to page 81. This question is there.
What?
It's in the
81?
book, Last year. Yeah, page 81.
Which one?
This question.
What?
Oh, brilliant, bro.
He was
Okay.
asking. He was asking if he could find this question in the book. I was just telling him the page number. It's okay. It's okay.
It's okay. And you there? And this table is the equations for the effective error A and the effective section modulus W. And I can say this for you, but the handbook is too thick. I can't send it to you. Okay, so
We have the book. We have the book.
okay, you can say there. Well, let me find. Okay, there is from the handbook. Okay, the handbook, and this is for the major diameter M 60, and then it's the corresponding minor diameter. In our example, should larger than 12.7 millimeter. and this is larger than the calculated D1. So we choose this the major diameter, of course. Because all the bolt is standard, and we use the major diameter. Use the major diameter to describe them. For this M. For this, okay, no. This, the number is the Miller major diameter, okay? And and today's class is very difficult. All the examples are very difficult too. So
Yes, Lord.
very difficult. Yes. So you should review these questions by yourself after class. Okay.
Okay, Lord.
Okay.
Yeah, Lord.
So this is all for today's class. Okay. The class is over.
Okay, Lord. Thank you.
Okay.
Okay, thank you, Lord.
Bye-bye.
Okay. Okay. Bye bye.